So in this illustration, we're going to demonstrate how we can actually have two separate things happening. One, the attitude dynamics is going to be controlled with its usual attitude differential equations, but the orbit, instead of using orbital differential equations, we're going to prescribe the orbit from a prior mission. So in this case, the Hubble mission. We're going to grab that from SPICE. SPICE can provide not only planet states and moon and comet states, but also spacecraft states as a SPICE kernel. So that's going to illustrate this. So the internal integration still happens, but then the final output is overwritten by what the SPICE interface provides. So how does that look? Let's examine the full simulation scenario. This will be a single process, single task, everything running at the same rate. We're going to run SPICE interface first. That's going to be important because we need to override the spacecraft position. So we need to know the current Hubble position and set it when we integrate here. And SPICE will also output Earth. So as we've done before in earlier scenarios, that'll create the Earth's location. The rest of it looks pretty much like code from the scenario attitude feedback, where we do inertial 3D pointing. Just stabilize the graph to point at a particular location in the sky. And then the control torque is an external force torque module coming from MRP feedback. So the difference is really is the SPICE interface addition, and we're going to hook that up. There's an optional input message for spacecraft that will allow us to dictate where the spacecraft is and override the internal dynamics. This can be done here for spacecraft, but you could actually also do it for the attitude if you wanted to. You could create an attitude description where the orbit is the real thing, but the attitude is prescribed. That's actually handy as well. So either could be done. Let's look at the Python code. So here, the usual imports, pretty much like scenario attitude feedback. And what is new is that we do have SPICE included in here. Let me just, why is that not working? There we go. Get everything going. Well, that comes with the graph factory. We have SPICE actually already included. I was curious where it was. Okay, so single task, single process. We set up Basilisk. We are having a 10-minute simulation. We're doing 10 hertz, so 0.1 second update rates. We create that task and process and combine it all, same as normal. Now we're making a spacecraft object. I'm calling it Hubble. I could have called it Janet, doesn't matter. Set up inertia, mass, and same as before, creating the graph factory, set up Earth, that's all cool. And then I add all the graph bodies to the spacecraft. So nothing novel here, same as earlier stuff. Now we're going to use SPICE. So as we had earlier, when we use SPICE for orbits, for dictating where different planets were in a multi-gravity problem, multiple celestial objects problem, I have to set up an initial time string, which I'm specifying here. And then I'd use the gravity factories create SPICE interface. It'll make the SPICE module. It will set this string. It will actually create an input message for or it's the standalone message for the epoch time. So it does all of this stuff. I want 0 base to be Earth. So that's cool. Here's the new stuff. You do need to create, it's handy if you create SPICE first, and it will add all the planet states that we specified, in this case, Earth. We want to now separately specify that we have spacecraft names. And in this case, there's a list with only Hubble Space Telescope. That's how SPICE identifies the Hubble. So we create that list. Then there is SPICE object.add spacecraft names, and you have to provide it the list, or actually it's a standard vector. We're converting it via SWIG into a standard vector, this list. And we provide this. So this now specifies which spacecraft SPICE should have provided the right outputs states. The next thing is we need to make sure SPICE actually knows about the Hubble. That means we have to be sure to have loaded up the Hubble's SPICE kernel. So that's this HST, Hubble Space Telescopes edited.BSP. And I'm giving it the path. That's where it's included in the Basilisk repo. The command is load SPICE kernel. That's something we have to do then to actually load that one up. And so When we call this command, it loads up already all the standard kernels that tell us where Earth is and a variety of other standard planets. So this one just loads an additional set of an additional kernel on top of the rest. So now Spice knows about Hubble. Cool. The rest of it, we're starting adding these things to the tasks. So we want Spice objects to run before we run Spacecraft object, because we're going to connect the output of Spice objects, the Hubble Space Telescope states, as an input to Space object. So it's important that that occurs first before we call Spice object. So I'm not adding priorities. That's another way to switch orders. I'm just, first in, first executed. So I'm adding the Spice object first to the task, then the Spacecraft object. The rest of them, this is very much just like the scenario attitude feedback. We have an external force module. We have a simple nav module, flight software, inertial 3D, attitude tracking error, and MRP feedback control, just configured. That's all the same. We make our standalone vehicle configuration message, which has the inertia. Subscribe that. In the end, down here, we connect everything. So that message is connected to MRP feedback. Simple nav is connected to the spacecraft object state output. But now what's different in this one is this line. You can see here, spacecraft object trans ref in message subscribe to Gravity Factory Spice object. So the Spice object has these output messages which tell us where's Earth, where are the other planets if we added other planets. But also there's a separate output message that will be set up if you've added spacecraft names. It'll create one output message per spacecraft name. If I had 3 spacecraft, Bob, Fred, and Harriet, then 0 would be Bob's, 1 would be Fred, and slot number 2 would be Harriet, and in the vector of output messages. So let's see how that actually comes together. So here we're creating this things, and these are the standard output messages, the Spice time output message, the planet state output messages. That's typically what we connect to if we want to know where is Earth, where is Mars, and so forth. These other 3, these really have to do with spacecraft. So this one here is a full spacecraft state. You might have a scenario where you don't even have a spacecraft state, spacecraft object. You're just prescribing the Hubble, the orientation, and the position at every time step. And you want this Spice interface to take that information from JPL Spice library kernels and create the spacecraft state message. So this is the full states message. The other parts are really the reference messages, because sometimes we have attitude reference messages, like with the guidance modules, that'll tell us you want to be lined up with the hill frame. This is the hill frame. This is your reference frame at this point. So it takes the same information that goes here, but it has both position and attitude and everything mixed into an attitude reference message, and the translational parts go into a translational state message. That's the one we're actually using here. And you can see it has the RN, so your reference position, reference velocity, and reference accelerations all provided there. So where were we on the code? So the spacecraft object, that's an optional input message, as we described. And if you specify it, it will override. So let me go to spacecraft module, because that's what we're connecting to. Module spacecraft, here we go. And you can see there's 2 optional. There's an attitude in at ref in message and translational ref in message. That's the one that we're connecting to here. And so Spice provides this as an output. We just have to make output connect with input on the spacecraft object. And that's what this line does. The rest of it is sets up logging, sets up the initial conditions. I don't have to specify initial position or velocity. I can leave defaults, because every time step, this is going to be overridden by wherever Hubble was in the Spice kernel. I initialize, run the simulation. At the end, since I custom loaded, if you do want to be a good citizen and not have a memory leak, since we loaded the kernel, we should unload it. The standard Spice things will be unloaded as well. Actually, I don't see myself doing that. I probably should have. Anyway, this is a way to custom unload the library that we did load up in this particular scenario. Okay, so that's it, really. The key is this line, you can override the spacecraft's position through a reference input message. And here we're using Spice to generate that reference input message. But really, you could have generated this reference input message from any other module that's capable of doing this. And you can do the same for the attitude. So you could have something else drive the attitude. So just as a general idea, let me go back to our scenario that we had. Here we go. So here we're doing attitude 3D, right? And I am making this reference, I'm using a force and torque, an MRP feedback loop, so there'll be proper transients and it will track it. If you didn't care about transients and you just want to go, you know what, if I'm simulating the feedback control, I can only simulate with a small enough time step so I don't have digital instabilities occur. What if you wanted to take 1 minute time steps? Then this control wouldn't work because that's way too big a time step for this for these gains to work out. You could just take inertial 3D, take its reference and actually connect it directly into the spacecraft. And then every time step, it would just point to wherever that reference is. Now, inertial 3D will look very boring. It'll just slap the spacecraft pointing in this one direction and then hold it there. If instead you would use something like hill pointing, where you would line up with the hill frame, the spacecraft would automatically just follow that hill frame orientation without having to have feedback control. That's handy sometimes when you want to take bigger time steps. There was one scenario looking at differential drag, and we wanted to have faster, drag. You hold an attitude for quite a while, then slowly change it to do some, orbit maneuvers. And so there we could just use whatever attitude reference the drag modules created and feed it directly into the spacecraft. And there too, it would actually just prescribe the attitude motion instead of using the internal dynamics. So that's kind of the big gist of this scenario. While we have differential equations, we don't necessarily have to use them. You can override either translation or rotation, or do both, override both of them if you wish as well in these kind of configurations. So anyway, hope you enjoy.